In order to calculate the average value of output voltage, we need to go back to slide number 7. This is the output voltage obtained, and I want to calculate the average value of voltage obtained at output. So I want to so in order to calculate the average value, I will consider this ripple. The limits for this are from 30 degree to 90 degree. So I will calculate the area under this curve and then divide by that integral by its time interval, so that I can get the average value. Now the same thing has been done over here, is that integrating the expression V is equal to Vm sine of omega t with respect to d omega t. Basically omega t is equal to theta, and the limits are from 30 degree to 90 degree. These limits are used in radians rather than using degrees for simplification. So if we go back at that slide, we see that this ripple is due to the voltage due to the two phases VAB, and we discussed in our first slide that in Y connected source, the line to line voltage leads the phase voltage by 30 degree. So that phase shift has been incorporated over here, and when integrated and divided by this term, the final expression that we get is VDC is equal to 300√3 by pi Vm. And similarly we can calculate the RMS value, and RMS value can be calculated by taking the same expression, taking its square. You see over here the same expression has been used, its square has been taken, then the integral will be solved, and finally we will take its square root. So the expression, the end result that we will get is Vrms is equal to 1.6554 times the phase voltage. In order to calculate the IDRMS, we need to see the waveform of the current shape from a diode. This waveform shows the current being drawn from the current passing from a particular diode. We have a shape wave like this. So this part is similar to this one that we have previously calculated over here, and we have two such bumps over here. Therefore we have taken the same expression. Instead of using Vm, we are using Im because I want to calculate the RMS value of diode. The only change is over here that it has been multiplied by 2, because we have two bumps in the current waveform from the diode, and its periodicity is 2 pi. From the 2 pi time period, this waveform only passes once. And here Im is equal to under root 3 Vm by R. Now in order to see the current RMS value of current drawn from the transformer, it can be again calculated by seeing the shape, the current waveform this is the current waveform from a particular phase of the transformer. So we have two such waveform like this over here. We have two bumps over here and two over here. So our area should be 4 times the area of this VAB. So for that, the factor of 4 is being multiplied, and the time period again is 2 pi. So overall the result that we will get is 0.78031 3 im, and im again is equal to under root 3 by r Vm. So IDC at output is equal to, we have calculated the VDC, so we will divide that VDC by R, so IDC can be calculated. And now we have 6 diodes and 3 pairs of 2 diodes. We have 3 pairs of 2 diodes in this case. When we had in a full bridge single phase full bridge rectifier, we had 2 pairs of 2 diodes, and now we have 3 pairs of 2 diodes. So in that case, the average current passing from a particular pair of diode was IDC or I naught by 2. But now when we have 3 pair of such diodes in case of 3 phase rectifier, so the value of output current IDC will be divided by 3, and peak inverse value has been already discussed, which is under root 3 times Vm.